Hi everyone, my name is Varun. Like Alvin said, work with Geert and Alvin. I will be presenting some some preliminary work which we've been working on simplicial complexes, right? Oh, yes.
The regular graph that you show.
Yeah. I could not I could not find a GIF. I could not find a GIF which maybe that could be one of my contributions. Yeah. So essentially this is just a preview of what I will do in the next 15-16 minutes, is introduce to you very quickly what simplicial complexes are, uh, present to you a general problem formulation, and then tell you how we propose to solve it, why we think it works better than existing methods, and hopefully we see that from the results as well. So very quickly, everybody already knows what are graphs, a set of nodes and connections between them. Every edge connects a pair of nodes, but a hypergraph generalizes the notion of edges to hyperedges, where edges can connect now not only two, but more than two. What is a simplicial complex? A simplicial complex is a hypergraph with a certain structure. And the structure is that for every group of connections, all the subgroups are also present in the complex, right? So for instance, I have a normal network, right? So a hypergraph can have a group of 4 as well. But there is no criteria that just because the group of 4 exists, that the groups of 3 also must. But that is true in a simplicial complex. So if I have a group of 4, then the 2 triangles also must exist. There are only 2, but yeah, there need to be the others as well. So every hyperedge is what we call a K-simplex. So 0 simplex simplices are nodes, a 1 simplex is an edge, 2 simplex is a triangle, and so on. And then in this work, although in principle you can generalize to any level, in this work I will focus on only edges and triangles. So what is a K-simplicial signal? So basically we collect a vector on every K-simplex, and we have a matrix of nk cross fk, where we have the number of simplices times the feature dimension on that simplex. How do we represent these simplicial complexes, right? So we have these linear maps called incidence matrices from sort of a k simplex to the k plus 1 simplex, right? And they're essentially just a matrix of, say, when we focus of nodes and edges, we have nodes cross edges, and then we basically assign a 1 in every column for the nodes that belong to that edge. And then, of course, we have a minus 1 because we assume a certain orientation, and that goes for the same for triangles as well. Except now we assign an orientation for the triangle, and if the orientation for the edge we decided here does not match, then we put a minus 1. So how do you represent a simplicial complex entirely? Is via these Hodge Laplacians, which is generalization of these graph Laplacians, right? Which is simply a sum of these incidence products. And then they sort of represent something called a lower Laplacian and upper Laplacian, which is basically the neighborhoods of a K simplex. And what are these lower neighborhoods? So consider an edge. So its lower neighbors are all the other edges which have a common node with that edge. So if you consider this, then these are all lower neighborhoods. Upper neighborhoods are other edges, which is part of the same triangle. So depending on which level you use to find the neighbors, we call it either a lower neighborhood or an upper neighborhood. And then most importantly, for a simplicial complex, so remember I said if a triangle exists, then all the edges must exist as well. We represent via this boundary of a boundary must be 0 constraint. Now the core difficulty in simplicial complexes difficulty in finding a simplicial complex is imposing this constraint, which is what we deal in this work. So what is the goal? I have some data. I want a simplicial complex, right? There is so exactly that. This is the general problem formulation, right? So we have some components that go into this. We have a link between the data that we have and the topology. We, of course, want to find the topology. And then I say I want to find my incidence matrices which are feasible. And this also involves a minimum number of edges and triangles. because I don't want to find an empty simplicial complex. And of course, I need the inclusion constraint to say if a triangle exists, all the edges exist as well. So I will go through each of these parts. Let's focus on maintaining feasibility. This was introduced in this paper. So we don't learn incidence matrices themselves because that is difficult to do because you need to maintain the structure that we talked about before. We select simplices from a full simplicial complex, right? So we have these full incidence matrices of time of shape, number of nodes and number of all possible edges. And then we have the number of edges, all possible edges to number of all possible triangles. So whenever you see a bar, it means we're talking about a full simplicial complex. We only have binary vectors which simply select which edges and which triangles exist, right? So if I have edges and triangles selected, I start with the full simplicial complex. I just select which ones exist with S1 and S2. And of course, we work only in the space of S1 and S2 because that means that we already guarantee that my instance structure is maintained. And then when I said we need a minimum number of edges and triangles, that means I have the simple minimum cardinality constraint on S1 and S2. So the next part of this problem formulation is the link between topology and signals. And if you notice, I put a little bar here on the edge signals, right? So this function couples my triangles with my edge signals. And I put a bar there because in this work, we assume that we have available to us all edge signals. So signals on all possible pairs of nodes, so on all possible edges. So that can be found by two ways. So either we don't have edge signals and we compute some product or some other permutation variant function to compute the signals on the higher order simplices, or we have a domain where we have access to all the signals on all pairs of nodes. So what are the standard ways that people link topology to signals, right? So the first one is the standard graph smoothness form. You have the standard the trace of the quadratic form, but notice I have my full Laplacian here, and that from the smoothness term on the full simplicial complex, I just select the edges that exist with the selection variable. For linking edge signals to triangles, one common notion is a notion of curl. So smoothness on the upper neighbors, the neighborhood that I mentioned before. So smoothness on the upper neighbors or curl is basically trying to check its consistency within a triangle. So it has to sort of be conservative within the triangle. So I have a plus, and a minus. So I have everything conserved within the triangle. But a small contribution in our work is why not go beyond? So this does not measure how close edge signals are in a triangle, right? So we introduce a new notion of similarity, which basically generalizes node signal smoothness to higher order simplices. And so I have over all triangles, I select whether the triangle exists or not. And then for every triangle, I basically sum the differences of all the pairs of edge signals. F here is the faces of a triangle. That means all the edges. Notice that all the selection variables are linear in the smoothness measures, and this will come up very soon. Now, this is the crux of the work of enforcing inclusion, right? So we need to ensure that the complex we learn is indeed a simplicial complex, right? So there are two main approaches that is currently followed to maintain inclusion. The first is hierarchical. So I will solve for my edges, and then I will see which triangles are possible, right? So I will solve for my edges, and I will see which triangles are possible, and only one is possible here. And I will just fill it up, right? Of course, only one was available here, so we filled up one, but you must fill in a certain number from the set of feasible triangles. So here there is no with the selection vectors, they introduce a bilinear constraint, right? So quickly, what does this mean? So pay attention to this vector B2 plus S2, right? So B2 plus is the same B2 that we saw earlier. So instance matrix from all possible edges to all possible triangles, with the plus basically meaning I don't have minus ones anymore, right? So this B2 S2 vector basically for every edge, it just counts how many triangles that edge is involved in. right? So for triangles, so edges 1, 2, and 5, it is basically involved in one triangle. And 1 minus S1 is basically, yeah, if that is still alive. Oh, yeah.
Take one side. Same thing.
Yes.
Sure.
I was a bit worried I broke it. So is that involved in the proposal? Great, thanks. I will pick this side. So B2S2 basically counts for every edge, how many triangles that is involved in, and 1 minus S1 basically inverts the selection vector. And this means that basically for everywhere that my edge does not exist, I need that edge to not participate in any triangles, right? Very simple. But the problem is it's bilinear, right? Which means if you put it in an optimization problem, you need to alternate. So what we did is we noticed that there is actually a slightly simpler way to enforce inclusion via a linear constraint, right? So we still work with the vectors that you saw previously. And what do they mean? So I have a vector which represents for every edge how many triangles it is involved in. So and this is my edge selection vector now, not the inverse, not the edges that don't exist, but the edges that exist, right? So everywhere that there is a non-zero value here, I basically need a 1 there. And if that is true, then my inclusion is maintained. And that is done by writing S1 greater than alpha B2 S2, and alpha has to be small enough, and small enough is another discussion. But if alpha is very small, then wherever I have B2 S2, say I don't know 3, then we have then if this constraint needs to be maintained, then we need to put a 1 there, which means that the edge exists, right? And now we can solve jointly without alternating. And then we basically started with a general problem formulation, and now we filled in all the pieces. We have the smoothness measures for F1 and F2, and then we have the inclusion constraint in the form of S1 alpha B2 S2. And then the rest is just bookkeeping. So S1, S2 are binary vectors, and then I have this minimum simplicity selected as well. What do we compare with? We compare with the other approaches I mentioned, hierarchical. So we first solve for edges first, right? And then we restrict to the feasible triangles, and then we select within the feasible triangles the smoothest of those, right? But note that it is not necessary that we have C2 triangles to select, because I might not have that many feasible, right? So I have to relax that constraint and just select as many as available. The same thing we had in the single triangle we saw before, right? So if I have to select 2, I can't select 2. I have to select 1. And the other is the greedy alternating approach I mentioned. So we spoke about this 1 minus this bilinear term equal to 0. So what they do is they plug it into the objective, right? And now you can have a cost. And now you can have a cost for edges and triangles with inclusion in it. So this basically means that you have, for edges, you have a smoothness cost plus a penalty if it is belonging to a triangle that exists, but it is not selected, right? And conversely, for triangles, you have a cost with H2, but you also have a cost if that triangle exists, but the edges don't, right? And they solve it greedily, which means that they first select C1 edges, and they select C2 triangles, and then so on. So in simulations, I simply simulate I will go through quickly. Yeah, so I have a net dose Rayleigh graph. Yeah, I simulate by filtering white noise through the graph Laplacian of the ground truth. I have a set of feasible triangles now that emerge. I select half of them, and then on those as well, I repeat the same graph Laplacian. Now a different Laplacian. So there is a Laplacian associated with the new similarity measure that I mentioned as well, which I will not discuss here. But essentially, depending on which smoothness term you want in triangles, you can choose which Laplacian, and then we simulate. We have a simulated setup. So we have two figures, right? And the two figures correspond to which H2 you use, which smoothness you use. So it doesn't really matter which one in the end. So let me quickly explain the results. So I will just explain one of them. So we have in blue the joint for triangles and edges, and we have the two benchmarks as well. And then we see that we perform really, really well. And one question is why are the two similar, right? Why is the greedy the same as the hierarchical? And that is because the penalty on the inclusion in the objective that you saw, the gamma, we set very high. And that means that once you select the edges, and then you go to select the triangles in the greedy method, the weight or the penalty to select a triangle that is not feasible is so high that you simply don't. And that boils down to the hierarchical. Now, is that the most fair way to treat it? Perhaps not. Mhm.
Then you also generate the data accordingly.
Yeah, of course. Yes, indeed. Yeah. So yeah, depending on, yes, yeah.
That's why
Indeed. So depending on whichever prior that we test on the algorithm, that is how the data is generated as well. And now on real data, right? So we stick to co-authorship data where my nodes are authors, and the node signal is basically how many times they use a keyword. Edges and triangles are authors of the same paper. So if three of us make a paper, write a paper together, then all the edges exist as well, and so does the triangle. I form edge signals by some invariant permutation invariant function of the node signals. Here I choose minimum. And then, so what we observe from the data itself is that the edge signals are not low curl, as I mentioned before, which you can imagine, right? Why would frequency counts of authors of keywords be similar to each other? I mean, be closed in a triangle, but they are indeed similar, which you can imagine is true. Right? So on a paper, all three of them, if three people write a paper, they have similar fields, which means they have similar keywords. And this is important to note that the prior of having low curl is not true on this real data set, but high similarity is. A lot of lines. I will go through them slowly. Disclaimer, when we assume low curl and we solve jointly, we perform horribly. So the edges and triangles, this triangles? Triangles are very poor, edges are not so bad. And this is because the prior on the triangles is violated, right? Whereas the prior on the edges was fine. It is indeed smooth, but it's not low curl. So we get terrible results. But then the question is, why do we not get terrible results with the benchmarks, the hierarchical and the greedy? And this is also why in the previous slide we get better results, but this is the same reason. So essentially what happens is in the hierarchical, you are always distracted by feasibility when solving for higher order simplices. So you will always look at the feasible set and choose within them. And you will never select a simplex which is outside this feasible set. And you're always almost distracted by the feasibility. And why I say always, almost always, is because in the greedy, you are not, right? So in the greedy, you always choose C1 and C2 triangles. And so if they are not feasible, then you still choose some infeasible ones. But mostly you still stick to the feasible sets, right? And why do you mostly stick to the feasible sets? Is because the cost is so high on the infeasible ones that they always outrank the feasible ones. So the moral is basically when you follow the prior, we perform very well. And this is because we don't have the reliance on feasibility, right? You can, and on the hierarchical and the greedy methods, even if the data prior is violated, then you can still rely on feasibility to choose at least a few correct ones. So in the end, it is how you think about what is an advantage, what is disadvantage. You can think that, yeah, in the greedy and hierarchical, the prior of feasibility is indeed some sort of regularized, right? So you stay within the feasible set. So to conclude, we designed a linear inclusion constraint, which is the crux of the work, which now allows you to solve jointly and now allows you to solve for edges and triangles all at the same time without looking backwards always. The joint method truly reflects if uh, the data follows the prior or not, right? Because we saw horrible results when the prior was violated, whereas before we never realized that. We don't really look at the smoothness, we look at feasibility instead. Future work is many multi-directional. One is, of course, extending to a weighted simplicial complex. And the reason why that is important is that constraint is not very meaningful when you have weights now, right? Because you have that alpha B2S2. What does that mean? Now you constrain that my edge weight has to be alpha times the sum of my triangle weights. Yeah, that does not have a very nice meaning. Of course, involving time varying topology, so having memory as well to track in topology over time is one. Another could be to also see if there exists. This is indeed a mixed integer linear program, right? So a binary linear program. So indeed, yeah, it is combinatorial. But as far as we know, so far that is one of the only way to impose hard inclusion, and we are still looking into ways of seeing if there is a way to include continuous variables and still enforce hard inclusion. And yeah, thank you. That's it.